Now let's discuss some of the vocabulary of blockchain. So one of the word that we hear when it's come to the blockchain is a genesis block. So what is a genesis block? A genesis block is the first block of the blockchain and is always hard coded. So a genesis block makes the foundation of your blockchain. You can define some of the characteristics of your blockchain in the genesis block, like what type of consensus algorithm that are going to be used in your blockchain, and you can also define some pre-mined currencies. Now what is a block? A block is a container data structure which store transactional as well as non-transactional data. Blocks are organized into a linear sequence over time. A block contains so many type of information. One of the information is a block number. A block number is the index number of the block from the creation of the genesis block. That means if the block number is 50, then it is the 50th block from the creation of the genesis block. One of the attributes of a block is nonce. A nonce is a 32-bit number which is adjusted by the miner in order to create a valid hash of the block. It is practically impossible to predict which nonce will result in a valid hash of the blocks other than brute forcing it. One of the attributes of block is a previous block hash. A previous block hash is the hash of the previous block. So if you are on the 50th block, the previous block hash will be the hash of the 49th block. And when you are in the genesis block, there is no previous block associated with it. That means the hash of the previous block will be all zeros. One more attribute of a block is the timestamp. A timestamp is a time which is determined by the miner, which is generally a time at which the block is validated by the miner. One of the attribute of a block is a Merkle root. So a Merkle root is basically a hash of all the hashes of transactions present inside that block. So if we have 8 transactions present inside a block, so the Merkle root will be a hash of all the 8 transactions. Merkle root also provides the immutability attribute of the blockchain. Now let's picturize it with an example. Now let's see how does this Merkle tree is formed. So a Merkle tree is a tree in which every node has 2 childs. So let's assume you have 4 transactions in your block, which is transaction 1, transaction 2, transaction 3 and transaction 4. So these 4 transactions are being taken and then hash of these transactions are being taken. So hash is being calculated for the transaction T1, for T2, for T3 and then T4. So after the hash of all the leaf nodes are being calculated, so all the transactions are basically all the leaf nodes of the tree. Then they are being coupled into a pair. So the hash of T1 and T2 will be taken. So this will be a hash of T1 and T2 and then you will have an hash of T3 and T4. Now again the hash of these two is taken. This hash is taken until you reach a parent node. This procedure is being carried out until and unless you reach a parent node which is an hash of all the transactions that are present inside that block. And then this node is known as Merkle tree hash. And then this parent node is known as Merkle root. So now why this is required? This is a very important question. One of the key factors of why this is required to reduce the size. Let's say if we have 100 transactions in a block or if we have 50 transactions in a block. So if you see from this point of view, even if we have 100 transactions in a block, even if we have 50 transactions in a block, we are going to have only one Merkle root. So irrespective of the number of transactions in a block, you are going to have a single Merkle root and that Merkle root is being stored on the blockchain. Another factor is this provides some security. Let's us assume that in T1 we had a transaction in which A had sent 1 Bitcoin to B. So this was a transaction, let's say in the 100th block. So in the transaction T1 we had a transaction in which A has sent 1 Bitcoin to B. Now an attacker comes and he tries to change this transaction. So let's see what will happen if he tries to change this transaction. So let's just say he said no, A has not sent 1 Bitcoin to B. He has sent 2 Bitcoin to B. So what will happen? The hash of this transaction will get changed because there is a change in the data. Now if the hash of the T1 is changed, correspondingly hash of T1 and T2 will change and then correspondingly hash of the Merkle root will get changed. And if the hash of the Merkle tree is changed, then the hash of the block is changed.